Now, this next talk is something special. It's a topic that we've only explored once in the past, but the speaker that we're about to have on stage, I have known for more than a decade. And this gentleman, this young hacker, this young buckaroo, I met him for the first time at a crypto party in downtown Tel Aviv. Anybody here ever been to a crypto party? So crypto party, it's not about cryptocurrencies and it's not about bitcoins. It's actually about exchanging your encryption keys in person so that you can trust the other guy. It's about setting up encryption on your computer and teaching other people how to use cryptography. So it's a pretty awesome practice, and it was a fun party downtown Tel Aviv. Now, Yuval Adam is an independent technologist. I think that means he's a hacker. And he likes to play around with things, including radio waves. So Yuval is going to help us decode the black magic of radio waves. What a perfect talk after talking about Harry Potter. Give it up for Yuval. Yuval, it's a pleasure to have you on our stage.
Thank you, Kellen.
Yeah, let's smile for the camera. Where is
cameras.
it? Okay, he's on break. It's okay. He'll be back when you're done. Don't worry.
We'll get our picture
and
later.
I'll be back with a drink as well.
Perfect.
All right, Yuval.
Thank you very much.
You need a clicker?
Yes, I definitely need my clicker.
Okay, don't forget it's not a gift.
Okay. So you want it back at the end.
Yeah.
So let's see. Yeah, this works. Okay. So hi everyone. It's great to be here. My name is Yuval. In my day job, I do consulting with large companies and small startups. But in my spare time, like Alan said, I like to play with all sorts of technologies. And radios are definitely one of my biggest hobbies, which is why I'm very excited to be here giving this talk. And I'd like to start off with a story. When I was 9 years old, I was visiting my grandparents' house. And as kids usually do, I was looking for things to play with. And I found something that fascinated me. I found an analog shortwave radio receiver. And I remember taking it outside with my best friend, and we were sitting outside in the backyard, playing around with it, tuning around, listening to all different kinds of music stations. And then we stumbled upon this.
Oscar, Bravo, Zulu, Victor, India, Foxtrot, Delta, Alpha, Mike.
So this voice sounded so strange and mysterious to me. It was obvious that this wasn't any regular radio station. It would sound very weird. And it immediately sparked my curiosity. And in retrospect, I think it planted the seed for lots of the work that I do today and lots of things that interest me. So in this talk, I'd like to share some of the curiosity for these magical fields of energy that are all around us. So radio is the technology of signaling and communicating using waves of electromagnetic energy. And it's the main physical phenomenon that humanity uses in order to communicate wirelessly over long or short distances. So it quite literally is all around us. Now, while the physics of radio are pretty complex, we don't really need a physics degree in order to understand kind of the basic core idea or the basic principles. And I find this beautiful animation to actually be very intuitive. So if you consider a wave of energy coming from a transmitter in your direction, as that wave passes through a conductive antenna, it's inducing the electrons in that antenna to create a small electric charge. And we can measure that charge and reproduce the signal as it was transmitted to us. And that's pretty much all the theory that you need to know about radio, at least for this talk. Maybe you want to go do a PhD about that, that's something else. But for now, this is everything we need. So the main topic that I want to introduce today, that some of you may have already heard of, is called software-defined radio, or SDR. In the past decade, the field of SDR has exploded and made radio much more accessible to large crowds, to developers, to researchers, and to hobbyists. Lots of different crowds are playing with this stuff. And to understand SDR and why it's such a powerful and transformative concept, I think it's much easier to first understand how a hardware radio actually works. So let's take this radio receiver as a classic example. Hardware radios are single-purpose devices. They receive a radio signal, they implement the processing of that signal with analog electronics, and the only thing that this radio will ever be able to do is tune to a frequency and play back the analog sound of the broadcast. No matter how much you tinker with this device or hack with it, it won't do anything else, at least not significantly different. Now, to understand what's going on inside the device, I think it's very useful to look at a typical block diagram for something like this. So we have an antenna that receives the radio signal and generates a small electric charge, as we've seen. But that signal usually is too weak. So before any further processing happens, that signal needs to be amplified. That's the RF amplifier stage. After amplification, we apply some basic tuning and filtering. This usually depends on the station that you're listening to, for example, to the incoming carrier signal. And then comes the important part, the demodulation. So demodulation is what takes the incoming carrier signal and extracts the baseband signal from that. So let me give you an example. So consider an FM radio station that's broadcasting, let's say, a talk show on 100 megahertz. We know that the average frequency of human speech is somewhere around 100 hertz, or 100, 200 hertz, something like that. So the demodulation is what takes the 100 megahertz carrier signal and decodes the original signal from that, the 100 hertz baseband signal that we talked about. That's demodulation. Modulation, other way around. But for receiving, we're demodulating the signal. So once we have the original voice signal in hand, the only thing left to do is to amplify that signal once again, usually with a volume control, and then output it through the speaker for the listener to hear. That's a hardware radio. SDRs do something slightly different. So the first part of the signal pipeline is identical. SDRs are usually generic enough so that no matter what signal we care about, it's all the same to them. The difference is that instead of demodulating the signal, like we did earlier, the SDR digitizes the signal through an analog to digital converter. So what that means is basically we're taking the incoming analog signal, the wave that we saw earlier, and we're sampling it at a very, very high frequency, producing digital samples. That process is called IQ sampling. Those samples are then passed out directly to software for further processing. Now, once you give this some thought, it becomes obvious why this is such a huge deal. If you make your hardware stupid and generic enough, then you're turning your hardware problems into software problems. And we know for a fact the software problems are cheaper and faster to solve, right? That's the difference between going out and manufacturing a new hardware revision for your device and just pushing a firmware update. That's the power of SDR. So a little bit of context on how we got here. So SDR as a concept was initially developed in various commercial products during the 80s and 90s, but the real explosion of SDR as we know it happened in 2012, when a group of developers were looking into the RTL2832 chipset. This chipset was used in cheap USB dongles that were built for receiving digital TV broadcast. Here in Israel, it's Idan Plus. The developers discovered that the video decoding pipeline can actually be bypassed, allowing you to feed the raw signal directly into the computer. These devices are now known by their project name that was spawned off out of this, which is called RTL-SDR, and they marked the first time in history that an off-the-shelf device at a $20 price point was available to anyone and allowed anyone to connect their computer to radio waves. And needless to say that this sparked massive interest. So fast forward 10 years, we now have a multitude of SDR devices available in the market, anything from the cheap RTL SDRs and up to laboratory-grade devices that cost tens of thousands of dollars. There really is a device for any type of use case that you could think of. Now, I want to say one thing about layer 1 security, which might seem obvious, but I think it's worth noting, and that's the key difference. When you're using a wired connection, that connection is by definition confined to a physical space, right, to the cable itself. If you want to attack that physical connection, you either need physical access to the cable or a side channel to attack that. With wireless connections, we're by definition broadcasting and propagating our signal widely. So the only limiting factors here really are range for getting an effective signal, or directionality if that signal is kind of pointed in one specific direction or one specific sector, or any limitations on the antenna, like if you want to talk with a satellite, you usually need a pretty big satellite dish. Those are really the only limiting factors here. So now that we know how SDRs work and what they do, I want to show you a few applications of how they're being used. And one of the most prominent examples is tracking commercial flights. This is done with a relatively simple protocol called ADSB. which basically means that aircraft broadcast their exact position at all times for safety reasons. And the thing is that these signals are so ridiculously easy to pick up. You can do it with no more than the cheapest SDR you can find, zero computational power, essentially, and a homemade antenna that measures no more than, let's say, 10 centimeters in size. All these components together cost like $50, $60. Once you have all the hardware set up, it's time to run some software. And in this case, I'm using a popular CLI tool that's called Dump 1090. Once you start running it, you immediately start to see all the incoming data packets in real time as they're being transmitted from the aircraft around you. And of course, once you have these coordinates, you can also plot them on a map. With a simple setup like the one that I showed you, operating from a relatively open balcony in the middle of Tel Aviv, you can receive targets in ranges upwards of 350 kilometers. So this just shows you how easy it is to work with well-known signals. And in this case, ADS-B is broadcast from above, it's unencrypted, and there's well-supported software for it. But what happens if you don't have that luxury? Let's say you're doing some novel research on a new wireless device or inspecting like a widely broadcast signal that you have no idea where it's coming from. This field is called blind signal analysis, and I want to show you how that's done using open source software. So first of all, a small tip. If you're, let's say, researching a device and you do have it on hand, it will probably have an FCC ID. Every single device that went through the regulation process will have one of these. You can go on the FCC database, which is open, and see all the specs and lab reports for this device. So that will give you hints on what you're looking for in terms of frequency or how this device works. But we're here to talk about SIGINT, not about OSINT. So the real first step is to identify a signal of interest, and we usually do that with a spectrum analysis. Here I'm running a software called GQRX. Spectrum analysis means that we're looking at a waterfall view of the frequency domain, which is the horizontal axis in this diagram, over time, the vertical axis. And that will show you, so we're basically tuning the SDR to a certain frequency window, and that will show you the strength of each signal within that window. So here, the wider signals are much stronger, the peaks. After we've located our signal of interest in frequency and time, we need to start decoding it. Now, there are dozens of different ways to actually modulate a signal, and each modulation potentially has dozens of different parameters for how data is encoded within that. Specifically for things that we're discussing or that most of this crowd would be interested in, we usually care about digital data that's modulated onto an analog carrier. So digital data being digital data, that's kind of obvious, as opposed to, let's say, analog data, which is voice. And the analog carrier is the radio waves, which are a physical phenomenon, so they're, again, an analog property of nature. So digital data on an analog carrier. For most of the stuff, for most use cases, this is the stuff that we care about. So we can then use another open source software. In this case, I'm using Ultimate Radio Hacker, which is software that helps you capture specific signals and inspect them. And that would help us identify which parameters they use. So things like which modulation, which line coding they use, which baud rate, things like that. All of these things together affect how our digital signal is modulated and encoded onto the analog carrier. Once we've extracted a valid stream of bits, URH is also going to help us in doing analysis in order to understand the higher level data protocol. This might be a phase that more of us are familiar with if we've done low level work with protocols or things like that. This phase is where we might have to start dealing with things like checksums, forward error correction, and most importantly, encryption. So if our protocol is any good, this is the point where you start to see encrypted data and start to kind of probe how well that encryption actually works. And if we did everything like we should have, then we've completely reversed engineered our signal, and we can then take the knowledge that we have from there and implement a complete signal processing flow using a very popular tool called GNU Radio, which is a toolkit for signal processing. And this will give us a complete real-time radio application that we can then integrate into any other software stack. So that's kind of from A to Z the entire process of how we take an unknown signal and move to a complete implementation in software. There's one other very interesting aspect of SDR that I want to talk about, which is the ability to use more than one receiver. So we now have off-the-shelf devices that run multiple receivers all on the same hardware clock. And this enables really interesting use cases that aren't usually possible with a single receiver. And I want to show you two examples. So the first example is direction finding. If you're using multiple receivers, you can calculate what's called the direction of arrival of a signal. So this tells us not just how strong the signal is, but also where it's coming from. And this is kind of a type of war driving, if you're familiar with the term, that never existed before. It allows us to pinpoint signals directly back to where they are transmitted from. Another application is passive radar. In this method, we're using strong, well-known signals like radio or TV stations, and we're comparing the source signal versus how those signals bounce off of a moving target. Now, this uses some complicated math, but it gives really interesting results. This basically builds kind of a small radar station in your home, if that's where you're operating this from. So this allows you to track various different objects in motion, and in this diagram you can see like some vehicles or airplanes, things like that. Very interesting stuff. So the first question you might be asking yourself, because we've just discussed receiving up until now, so what about transmitting? What's going on there? The thing is that cheap SDRs you can't really transmit, at least not reliably. Which is not entirely true because there is, like, for example, a really cool hack that allows you to send dirty signals from a GPIO pin of a Raspberry Pi. I don't know if anyone knows about that. That's a really, really cool project. But higher quality devices absolutely allow for active transmission attacks. So this opens up a whole class of attacks, things like spoofing, replay attacks, man-in-the-middle, downgrade attacks, and denial of service. You can do all of these things if you have a transmitting SDR. And just to show one example, which is in the news, GPS jamming is absolutely a thing. Obviously, it's happening on a kind of military-grade scale, but it's happening, and you can actually measure that, like this website, which measures GPS jamming all over the world. It actually does that using data from airplanes that we saw earlier, which is kind of interesting. So that's kind of an example of kind of a military active transmitting attack. The second question that might be on everybody's mind is, if SDRs have been around for over 10 years, then aren't we stagnating? What's going to change in the future? And how is all of this really relevant? And there are many answers to that question. So we know several things. We know that wireless layer ones are still a viable attack vector that isn't going anywhere anytime soon. We're seeing more and more research coming out all the time that exploits various physical layers. And we know that SDR devices just keep getting better because we're seeing them come out in the market. They have better specs, they perform better, they're cheaper, so that's happening. We're seeing more open source signal processing tools with new capabilities, specifically around machine learning and deep learning of signals, which is a really cool thing. Essentially, there are some demos showing how you can pretty much, AI on signals. And we're seeing more and more clients using wireless infrastructure. So things like autonomous vehicles, drones, and satellites, when all of these are deployed, they're using the wireless spectrum and they're communicating over radio. And the last thing is the popularization of open source infrastructure stacks. So things like LTE or 5G, you can deploy those just using open source software. You can basically have your own LTE network within your home if you want to do that. It's a little bit complicated because the frequencies are regulated, but otherwise, in terms of software, it's possible. So there's lots of exciting advances, and the field is definitely expanding and improving. So to answer the question, all this stuff points to the fact that if we care about the security of our technology in general, we should be caring about how the technology that we are building is using radio. And SDR is the de facto way to do that, either to build a product or to research it. So I'd like to kind of end on the same note that I started with, and that is that the world of radio is full of mysteries to explore. And I believe that we're really lucky and privileged to live in a time where taking that journey is now available to everyone. Thank you very much.
We got a drink back there for you. I I know you
Yeah.
asked for a special red little drink we call
We're gonna-
Campari. Smile to the paparazzi. That's good. All right, so now I have a special announcement. Thank you so much, Yuval.
Thanks, Ellen.
We have speaker gifts and a drink and Campari for you back there.
Thanks.
Leave the clicker. That's not a gift. Okay.